What are some ways to name the same part of a whole? Think about this question during the lesson. James ate part of the pizza shown in the picture. He said 5/6 of the pizza is left. Cardell said 10/12 of the pizza is left. Who is correct? How can you tell from the picture that 5/6 of the pizza is left?
Well, when we look at this pizza here, we can see that you know, the denominator is going to be the number that makes up the whole. So how many pieces were in this pizza as a whole? And that's one, two, three, four, five, six. Pieces make up your whole. That's your six. Then your numerator up top is the number that we're talking about here. How many parts of the whole? We're talking about what's left of the pizza. That's one, two, three, four, five parts of this whole pizza are left. That's how you get 5/6 here.
In a fraction, the numerator is the number on top. The denominator is the number on the bottom. The denominator tells you how many equal parts there are. What does the numerator tell you? The numerator tells you how many of the equal parts are being talked about. The pizza was sliced into 6 equal parts, and 5 parts are still in the pan. One way to see who is correct is to use an area model. Draw a rectangle and divide it into sixths.
Normally, when we talk about area models, we're talking about either like an array or a diagram, but in this case, it just means a picture. An area model, we're using a picture, and that's really what we refer to often when we say area models, is using a visual, using a picture. And with fractions, it's going to be very helpful to draw pictures to compare your fractions or determine if they're equivalent, because that's a really good way to just visualize it.
Shade 5/6. Why is this area model labeled 5/6? The model has 6 equal parts, and 5 parts are shaded. Then divide the rectangle into twelfths. How many parts are shaded now? Select your answer.
So I just want to point out here that basically what they did is they took this same exact rectangle and they just copied it, and then they broke it up into even smaller pieces. The size of the whole did not change. The amount that's shaded in here did not change. The only thing that changed were the size of the pieces that make up the whole, because we split it into more pieces. So now my whole is made up of 12 parts instead of 6 parts. So that's what changed here. And then you can say now the amount that's shaded in changed, because now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parts shaded in.
10 parts are shaded now. Why is the second area model labeled 10/12? The model has 12 equal parts, and 10 parts are shaded. The number and size of parts differ, but the shaded part of each rectangle is the same. 5/6 and 10/12 represent the same part of the model.
So I want to point that out to you, because while we have 6 parts that make up the whole here, 12 parts that make up the whole here. I mean, you can see the line here to create more parts, but you can see that the amount that's shaded looks exactly the same. It is the exact same size. We have here, and then you have this way, you have this whole part shaded in. And here you have the same exact part shaded in, the same exact size. That's what makes this equivalent. It is the same size. It's the same amount of the whole that's shaded in. It's just written differently because the denominator is different now, and then the numerator is different now, just because of how we broke up this shape into more parts. But the amount that's shaded in is exactly the same. That's why we call these equivalent fractions.
They are equivalent fractions. Equivalent fractions name the same part of the same whole. Another way to see that the fractions are equivalent is to use a different area model. Draw a circle and divide it into sixths. Shade 5/6. How many parts does the circle need in order to show 10/12? Select your answer.
So 10/12, I know that 12 is how many parts make up my whole, right? 12 is how many pieces will make up my whole, so that's how I know 12 pieces are needed.
The circle needs 12 parts. Divide the circle into twelfths. Now 10 parts are shaded, so the circle shows 10/12. The number and size of parts differ, but the shaded part of each circle is the same.
So you can use different shapes here. It doesn't have to be a rectangle or a square. But again, they did the exact same thing. They just brought this same shape over and just split it into a few more pieces. So the amount that's shaded in did not change. It's still that same size. However, the number of pieces that are now shaded in changed because we split this into more pieces. So because we split it into 12 pieces, now you have 12 parts that are shaded in. So 12 parts is equivalent to 5/6 because they are the same part of a whole. Their size is exactly the same of the whole.
5/6 and 10/12 are equivalent fractions. Both James and Cardell are correct because 5/6 equals 10/12. Does it matter what shape is used to show each of the two fractions?
And like I just said, it really doesn't matter. You can do it either way. I think pictures are a great way to see that and to draw it out. So whether you want to use circles or squares or rectangles, it's up to you. As long as it is the same size. Notice how these rectangles are the same exact size. Notice how these circles are the same size. You can't use two circles like this. That would not work. And just bear with me on the circles here, but these, if you color in half here and then half here, both circles have a half colored in, but they're completely different sizes. You can't even say that they're the same. So if you're going to compare fractions or visualize it this way, you have to make sure that your whole is the same size.
No, either shape could be used as long as the same shape is used for both fractions to justify that the two fractions are equivalent. 5/6 of the rectangular model does not have the same area as 10/12 of the circular model. Now you know some ways to name the same parts of a whole.
I hope you liked working with these fractions.